Welcome back again to ESEM 2021. I'm Valentina Lenarduzzi from Aiuto University from Who Connected just now. And this is the third session that we have today related to defect prediction. We have two technical paper today. So I want to provide a stage to the first author of the day, that is Wang. Welcome, Song. And the title of the paper is Continuous Software Bug Prediction. Remember for the audience to provide your question in the chat in YouTube, and I will formulate at the end to Song. Song, the stage is yours.
All right, thanks for the introduction. Hi, everyone. Welcome to the talk. As introduced, my name is Song Wang. I come from York University. And today we'll be presenting our study, Continuous Software Bug Prediction. This work is done in the collaboration with Junjie and Gesi and Nagappan. All right. At the very beginning, I just want to give you guys a very brief introduction to bug prediction. Basically, in software bug prediction, we have two phases. The first one is the training, and then after that is the prediction. So in the training phase, first of all, we need to collect the historical files as a training instance. And then we need to label the file as clean or buggy. And after that, we need to extract the features to represent those instances. When the instance and features are ready, we're going to build machine learning-based card files as the predictor. Whenever the predictor is trained, we can use it to predict the new instance as buggy or clean. All right, this is the whole picture of bug prediction. And we have seen many successful bug prediction models from many large organizations, for example, from Microsoft, Samsung, Google. So, which means bug prediction have already play a very important role in the quality management in many large organizations. So, in recent years, we have seen many bug prediction models, and most of those models are evaluated on several widely used and well-known benchmark data. For example, the promise dataset. Although those datasets contain many different versions from many different projects, however, our menu analysis confirmed that those datasets contain randomly selected versions from project, which means they cannot represent the real-world continuous software bug development scenario. And the versions selected in those datasets often have skip. For example, between two versions of the Camel project in Promise, they can be up to 1 year between two versions, which cannot represent the real world continuous software development scenario. All right. So these issues of the currently benchmark dataset actually motivate us to explore answers to this question: how to conduct a software bug prediction in the context of continuous software development. To answer this question, our pilot study have actually identified two unique challenges of continuous bug prediction. So the first one is about the training version selection. As we all know, usually the project may have multiple history versions, which means we can use any of the history version as a training data. However, different training version could have significant different performance. So here we show two example projects, Camel and Lucian. Those are widely used in existing benchmark dataset. So what we do here is we use the 20 continuous versions, and then for the latest 5 version, we use it as testing data, and then we build a model with the training version from the earlier 15 version data. Here we show the performance difference based on AUC values, the absolute values of AUC. As we can see that on each testing version, the performance difference can be significantly different. So this actually raises the question that how to select the best version to build a bug prediction model in continuous bug prediction, given there's a large number of candidate versions. And then the second challenge is about the model update and reuse. It's widely known that the software bug prediction data suffer the constructor drift issue, which means the performance of bug prediction model evolves over time. Then we need to update the model, otherwise the model gonna lose the prediction power. However, we also find that the model does not directly lose the power. For example, and we still use Camel and Lucene. We collected 20 versions, and we use the first version as a training data, and then we use a model to conduct a bug prediction on the later 19 versions. And we can see that overall the performance of the model declined. However, even this decline, we can still use a model to achieve nice performance on some versions. Right. So the second challenge in here actually raises another question: is when should we update the defect prediction model? To answer those questions, we actually proposed a set of a solution to help the model building, updating, and evaluation of bug prediction model in continuous software development. The first one is about a training version. We propose a computer. And then after that, we propose a continuous update to help the developer to decide whether they should update or reuse the model. And then finally, we also evaluate a new effort where related model evaluation approach, which use the probability difference between different versions. You can go through our paper to see the more detail of each algorithm. Because of time limitation, we didn't give more detail here. So in order to evaluate our approach, we selected 9 projects, and they're widely used project from existing benchmark dataset. And then we build a AD tree based bug defect prediction models, and we use AUC and P of 20 as a metrics. To evaluate the compute, we select 5 versions from each project. So what we do here is we show how accurate our compute can recommend it the best training version. And we can see from the table around 80% of the testing version we can actually find the best training version. For the second research question, we evaluate our updated. We reuse the same testing data, that is the latest, and then the latest team version. And then what we do here is we try to use updated to decide whether users should update or reuse the model from the previous running. And then we can find the table also shows the result. As we can see, for 80% of testing version, we can find the best. We can make the correct decision. For the last research question, we compare our evaluation approach with the existing effort-aware bug prediction. On the testing data, we can see that almost on all the testing data, our approach can achieve better results. All right. This also confirms the effectiveness of our approach. All right. To summarize, in this paper, we conducted an empirical study to explore challenges in continuous software bug prediction, and then we provide approaches to help the model building, updating, and evaluation. In addition, we have also provided a new benchmark prediction data that contain 120 continuous versions. We hope this data can facilitate future continuous software bug prediction studies. Thanks all. Any question?
Thank you very much, Song, for your nice presentation. There are questions from the audience. So in the meanwhile that they maybe will formulate, I have some question related to the methodology that you use. So can you provide us some more, I can say, explanation related to how did you select this project? So why did you select this project? The model that you include, why do you include this model? And a little bit inside of the training phase, because it's the important part of your work.
Yeah, a good question. So we only use the 6 project as our experiment subject. The reason is because we try to cover, because there's a 5 different existing benchmark. We try to cover each of those benchmarks. Well, first of all, we look at the overlaps, and then I think there are more than 6 when we look at the overlap. However, we when we look at each project, we also need to get enough number of continuous versions, right? We select at least 20. So after the 2 different criterions, we only have 6 left.
Yeah,
Also those 6 projects are widely used open source project.
yeah, and then related to the model, why did you select this specific sort of model that you presented in your slide and the training phase that you adopted for training the model, of course?
Oh, in the pilot study, we only show 2 projects. In our paper, we show all the result of the project.
No, I related to the model that you used to
Okay,
perform
yeah.
your study.
Yes. For the model, I showed 83 in our experiment. We actually try 5 more other models, but 83 is the best one. So we only reported 83. In our paper, we show the comparison between 83 and other models.
Okay. Thank you very much for your explanation. There are some questions from the audience. No, so thank you very much, Song, for your nice presentation. And we can provide the stage to the sorry, that is Jiri Gesi. I correct pronounce your name. And so your paper has title, sorry, an empirical examination of the impact of bias on just-in-time defect prediction. So the stage is yours, Jerry.
Hello, yeah, thank you. Hello everyone. My name is Jiri Gesi, and I'm a PhD student in University of California at Irvine. This work is done with Jiawei and Iftekhar Ahmed. So defect existing in software could cause substantial effect on business and even on people's life. And just-in-time defect prediction technique is an efficient approach that can help developers and testers to quickly narrow down the most likely defective commits. And in past several years, machine learning, especially deep learning, further promote the development of the just-in-time defect prediction. However, prediction bias is a negative side effect of machine learning techniques. Bias in machine learning is a scenario that the prediction model's results are systematically prejudiced due to wrong assumption. Such as in object recognition, it has been proved that it is easier to detect normal vehicles than crashed vehicles. Since comparing to the volume of normal vehicles data, the data that contains crashed vehicles is far too less. And this kind of bias usually caused by using the data set that is imbalanced on some specific characteristics. However, we wonder if this kind of bias also applies to defect prediction models, so that part of defects are easier to be detected than others, or vice versa. So just-in-time defect prediction techniques relies on the quality of the data. However, data often exhibit highly skewed class distribution, which means most data belong to majority classes. In the contrast, the minority class only contains a small number of instances, which is also known as a few-shot class. This imbalance not only happens on defect and non-defect label classes, but could also on the commit characteristics, such as the number of lines added code or number of modified files in a commit. Few short class is always underrepresented during the model training. So the trained model often performs poorly on this few-shot class of datasets. Furthermore, researchers often demonstrate their newly proposed defect prediction techniques on different datasets. So it is important to evaluate the significant impact characteristics imbalance among different datasets to make sure a fair comparison. Researchers have been using two kinds of machine learning approaches on defect prediction. The first one is metric-based, and another one is using deep learning techniques to automatically extract semantic and syntactic structure of the code changes and commit messages to predict a commit is buggy or not. So in our work, we compared our approach with the DeepGIT and the CC2WAC. The research goal in this study is to explore the bias in just-in-time defect prediction based on various commit characteristics. So in this study, we answered these three research questions. The first one is, do commit characteristics have an impact on defect prediction performance? And then, which characteristics affect defect prediction performance the most? And the last one is, how well can deep learning techniques predict the defects by explicitly considering few-shot classes? So next is the methodologies that we followed in this study. So in the beginning, we choose DeepGIT and CC2WAC for deep prediction, as they have the state-of-the-art performance on defect prediction using deep learning. And we selected the OpenStack and Qt as learning datasets are very popular in defect prediction. Next, we selected the 5 commit characteristics to investigate, which includes file count, edit count, multiple comments count, in-word and out-word dependency count. Next, we investigated the impact. We investigated characteristics distribution between a difference between correct and incorrect predictions from DeepGIT and CC2WAC. So we split the correct and incorrect predictions from two models. Then we analyzed the commit characteristic distribution between these two separated groups. Next, we investigated the impact size of different commit characteristic on defect prediction. First, we split the datasets based on each characteristic, and we got 5 pairs of majority and few-shot subdatasets. Then we trained models on these 5 pairs of subdatasets. And at the end, we evaluate whether there is any prediction bias between those majority and few-shot pair subdatasets. The result in this step shows that the prediction performance on the few-shot subdatasets is much worse than majority subdatasets. So we proposed SafetyGIT for few-shot classes, which is a Siamese-based defect prediction framework to improve prediction performance on few-shot subdata sets. So the first step for SafetyGIT is to split the all data into majority and few-shot subdatasets based on significant impact characteristics. We continue use the original DeepGIT or CC2WAC on majority subdatasets, since it already get a great prediction performance on majority classes. However, in terms of few-shot subdatasets, we used a Siamese network-based classifier, since the Siamese architecture is specifically designed for few-shot learning. And then we got a specific few-shot class classifier for the few-shot data. Now I will show the results for research questions. So from this table, we can see the calculated mean values for file count characteristic is 2.71 for correct classification and 8.58 for incorrect classification on DeepGIT. We also used the Mann-Whitney test to validate the file count value distribution for correct and incorrect prediction instances. The result provides support that file count distribution is significantly different from correct and incorrect predictions when using DeepGIT. We also got similar results for other characteristics when using DeepGIT and CC2WAG. In summary, the deep learning defect prediction techniques performance are significantly affected by these characteristics. Now we want to get which characteristics affect defect prediction performance most. First, we need to split the data based on each characteristics. And for this purpose, we have to calculate a splitting threshold for each characteristic. The details of a threshold calculation is described in our paper. So here we can see the divide threshold. And after splitting on file count characteristic, we can see the majority class contains the instances that are below the threshold, which occupies more than 84% of all dataset. And the few shot class only contains 15.91% of all data. Similar pattern also applies to other characteristics. So now we train separate prediction model on each pair of few shot and majority class sub-data sets. So from here, we can see that our experimental result shows the performance of few shot class is much worse than majority class in terms of AUC for all characteristics, especially for file count, inward and outward dependency count. So the next question is if our proposed science-based technique, shifter GIT, could improve the prediction performance on few shot classes based on different characteristics. So we compared our shifter GIT with CC2WAG and CC2WAG oversampling on few shot classes. As the result shows that shifter GIT performance significantly better than the other two. So the result we got in shifter GIT, the AUC score is 69.19, and the original CC2WAG only got like 57.88, and we used the oversampling on CC2WAG, and it got 60.39. So our commit, our result shows that a commit characteristic imbalance leads to prediction bias. So, and our future goal is to improve the prediction performance on few short classes beyond the current performance of shifter GIT as the AUC. Since the current performance shifter GIT's AUC score on few short is still much worse than the majority part of the sub-data sets. Thank you, everyone, and I will be happy to answer any questions.
Thank you very much, Jiri, for your nice presentation. There are some questions from the audience. I cannot see a question right now, so I have one question related to the methodology that you apply. Why you specifically selected this deep learning model? You presented the list and you say at a certain point that you consider only this one. Which were the characteristics that you consider in this selection? So why these and not other?
Okay, so your question is like why we choose those two techniques and why we specifically select these characteristics, right? These two questions. Okay, so yeah, so our research is mainly on to like check what is the deep learning performance of like the bias in using deep learning, right? And when we go to do the like the literature review, we find CC2WAG and DeepGIT. These two are the state-of-the-art performance on the defect prediction using deep learning. So we use them, and we use the two of them because we wanted to have a comparison between them, right? And for the community characteristic selection, actually before we not only select these 5. So our methodology was like we go and check the papers that what kind of we go and read the papers that like how can we describe different kinds of bugs, and we find like a bunch of papers of that, and then we also find a lot of like characteristics actually. So in this presentation, we only present the ones that has a significant impact. Like during the correct and incorrect, we can see like there is a very big distribution difference. And also, like when you split based on those characteristics, we also see significant, like the performance drop between few shot and, like the majority. So we present those like these 5 most significant ones in the paper. But actually, before we have like about 12 characteristics selected.
Okay, thank you very much for answering to my question. There is one question from the audience formulated by Francesco Lomio. So Francesco is asking if you can, now I show you, if you can please clarify which type of validation has been used. Also, how could you explain a significant lower recall using the Sifter JIT compared to the CC2VAC?
Yeah, thank you very much. Actually, I expected this question. So first, the validation part, like you just use the, like we have the 2 data sets, right? And we split the, we did the cross validation, like for sure, like we did the 10-fold cross validation to make sure our result is stable, and we also run the cross validation like a lot of time to make sure we reported the average results in this like a paper. And for the recall part, actually our group also discussed that. You see, like from my result, you can see that okay. So for the recall, you can see my Sifter JIT drops like from to 30 over sampling also drops like like around 30. So for the original ones, actually, like so since for those few shorter, like the few shorter classes. So if you go and see the like directly jump to the result, you can see that actually, like what they do, like the original ones, they don't really learn any like representation for the commits. But what their prediction results is like they just give everything is like 0, everything is 1. Basically, if you see for the like QT, we find that okay. So if we have like they have like about 200 few shot class instances, and they just directly go and like predict all as a problem, all as like a defect, all as non-defect. So those kind of scenario. So they don't really do a like a prediction there. They just give all zeros, all ones. So then you can see but in our results, it gives like it does learn something and give the zeros and ones. So for the recall part, you can see that since our result is 0 and a combination, a lot of zeros and ones, then it makes our recall kind of like drops significantly, because we didn't really give the all zeros or all ones, and the calculation gives our really bad recall there. And I believe that is also the part that we should work more to improve the like the prediction recall on the like the few short classes.
Okay, thank you very much. Before concluding, I would like just to ask you if you consider some pre-filtering approaches before running your model. So, for example, if you remove the correlated variables, so doing some feature selection, because when you consider a lot of variables, there is the possibility that 2 or more than 2 are correlated between and among each other. Is something that you consider, or in case a suggestion for the future work?
That will be our phase forward for sure.
Okay, perfect. So, thank you very much for presenting today, for the presentation and nice answering. Thank you very much, Jiri. So I would like to conclude today this third section, sorry. And it's my pleasure to provide directly the stage to the last section of the day, that is based on registered reports, and the chair will be Jeff Garber. Thank you very much, and I hope to see you face by face next year. Bye.